All right, you guys, back to the loom video. So if we think about what we've been looking at, we've been playing around virtually with flames and catching different atoms. I shouldn't say on fire, it's not right. We have been exciting those atoms with either heat or electricity, and we notice that when we do this, they give off these specific colors of light. And if we had amazing light vision, we would notice, we wouldn't just say, oh, it's green light. Like I would actually be able to say exact what wavelengths of green light it is. And maybe there's even a yellow light that's in there that my human eyes don't see, or maybe even a purple light that's in there that they don't see. So you just got introduced through that video that you watched yesterday of the emission spectrum. And we looked at it for all of these different elements that were there. But think about what we're trying to make sense of. We're trying to go back and go, well, how does this relate whenever we take this atom, we energize this atom, and really what you're doing is you're energizing the electrons in the atom. If we were energizing the protons and the neutrons, then it'd be nuclear chemistry. You would morph into some crazy, strange radiated organism, and it'd be done. We're messing with the electrons, okay? A little bit safer to mess with, I guess. And whenever we excite those electrons, we notice they give off light. So what the heck's going on, okay? So there's some things we gotta process first in here. So if you get out your guided notes and you turn to page 3, that's kind of our beginning of what we're going to do. And the first thing I want you to do at the top of page 3, it tells you, let's brainstorm some key characteristics that we have observed when energy, whether it's heat energy, like in the flame test video that you watched, or electric energy, which would have been the video clip talking about the emission spectrum that you saw. What is going on? What are you seeing? Some key characteristics. So hit pause, just brainstorm some stuff that you've processed, okay, before we move on. I always wonder if you actually hit pause or you're just like, whatever, I'm gonna pretend like I did that. But if you did that, I'm really, really proud of you, okay? So yesterday, whenever you were watching the video and, maybe Ms. Merkus or I took some time to talk about that emission spectrum and what it looked like, we should notice that when we look at the emission spectrum of any element, there's dark areas and then there's these bright colored lines. So let's process what we mean by that. In fact, before we even do that, let's just do a quick little search here. Emission spectrum of, let's go helium. That's one of the ones that we were looking at. Okay, so let's take a look at this guy. So if I were to look at the emission spectrum here of helium, hydrogen's up at the top, but helium's down here, I see these specific colors of lines, and I see these black areas, okay? So this is what we mean. So this is called an element's emission spectrum. We need to process what we see here. So we've got the dark areas, which are the black areas, and then we have the bright lines, the colored lines, okay? So if we go back to this guy, the dark areas, so those dark or black areas, indicate energies that are simply not released when an electron jumps. So it gets excited. I give it electrical energy or I give it heat energy. So whenever it jumps from its excited state, I give it energy, it jumps to its excited state, but it doesn't like being out there. Okay, it's kind of scared being where it's supposed to be. And so then it wants to jump back down to where it was before. Okay, so it started off near the nucleus, like near its kind of home base. You give it this, it's like giving you kids those 5-hour drinks or something. Maybe you took like 15 of them. And if I tell you to sit in your chair, like I'm going to give you 15 shots of a 5-hour drink or whatever those things are called. And I say, no, but you have to sit in your chair. You'll be like, yeah, forget that. Like you take your little 5-hour drinks, next thing you know, you're zinging around this room, going everywhere. And eventually you decide, maybe I should sit back down in my chair. You're returning back to ground state, okay? So when we're looking at that electron and we've excited that electron, we've given it heat energy or we've given it electrical energy, It's like a 5-hour drink. It jumped up from home. It jumped away from home base where it normally is used to being in that electron cloud. And it kind of has fun for a little bit, but it goes, I'm a little nervous and I'd rather just go back to my home base. I'd rather go back to my desk and sit down. But in order to do that, it has to get rid of its energy. Like, how do you guys get rid of your 5-hour drink energy? You shake, you move, you dance. I don't know. You do all kinds of crazy stuff, but you have to release your energy before you're willing to sit back down and be chill. The way the electron releases its energy is light. So we give it heat, we give it electricity. It gets super excited to be like giving you caffeine. It jumps out, it goes crazy. And it has to let off that energy before it's going to go back down to its ground state, to its relaxed state. We see it giving off its energy in the form of light. You would give off your energy in the form of moving, shaking, running, jumping, singing. I don't even know what else you crazy kids do, but that's how you do it, okay? So when we look at the emission spectrum, and this is an electron that has been excited, it has been given energy, and then it's giving it off again, we get to do a quick little snapshot of, what did it do whenever it gave off that energy? What did it do? What color of light did it actually give off? And that's what the emission spectrum is. It shows you that color of light that it gives off. So now we're interpreting this color of light. The dark areas, the dark bands, are wavelengths of light that the copper atom, for example, or the helium atom, whatever it might be, can't give off that color. Just absolutely, it's just like it's a no-go zone. I can't even give off that color. The colored lines, the bright lines, okay, which is the next part, these colored lines indicate to us the quantifiable bundles of energy that are given up. Okay, so the quantifiable bundles of energy that are released when electrons move from that excited state in the electron cloud that is farther from the nucleus, so that's where it got its energy, it's way, way far from the nucleus, goes back down to its ground state that's closer to the nucleus. All right, so if we go back to, and if you got to hit pause, do, but if we go back to this picture, all right, so let's look at, in hydrogen we could do too, but I don't know. I like helium. It makes you talk funny when you suck it in. Yes, adults still do that sometimes, or just I do. So here's helium. We took a normal helium atom, boring, does nothing. I gave it electricity. That's like it's caffeine. I gave it a caffeine shot in the form of electricity. That sucker's excited now. So it's zinging around, it's moving around. The electron that just got tons of caffeine has jumped away from its normal electron cloud, had fun for a little bit, but it's like, oh, Mom, I want to go back home. This is kind of scary. So in order for it to go back home, it has to burn off its energy. It has to give off its energy. How does that electron give off its energy? Right here in the wavelengths, these different colors of light. So helium electrons are allowed to give off a single purple wavelength of light, some kind of, I guess we call this blue, green, yellow. Looks like there might be several wavelengths of yellow that are given off. There's some oranges and there's some reds. Okay, it's not allowed to give off. This is like the no-go zone. It can't give off anything between this yellow that goes from this yellow to this orange. It's not allowed to give off. Anything between this orange and this red, it's not allowed to give off. Anything that's to the right of this red, it cannot give off. It is only allowed to give off quantifiable, specific amounts of energy. This is like that dude in the video yesterday that said, imagine if your food was quantized. What if you weren't allowed to have just one bite of a hamburger? That every time we told you you're going to have a hamburger, sorry, dude, you got to have the whole thing. Like there's no just, can I have a bite? No, not an option. You can have the whole thing and that's it. Or you can only eat this small amount forever and ever, and that's it. Those types of things are not quantized. They're not packaged. These are packaged, okay? Now, how do we see helium? All right, go back to, let's do this type of thing. Emission, what do I want to call it? Spectrotube. I don't know, maybe it's one of these. Oh, here we go. Let's pick on this dude. So my human eyes see helium right here, far left, right? That's how I see helium. I'm like, oh, well, I'd call that orange. Now, something far better at being able to look at this compared to me looks at helium and goes, oh, sorry, Zelensky, I know you thought you had good vision, but honestly, there's some blue light that's hidden in there that's given off. That's purple, sorry. There's some blue, there's green, there's yellow. Now, I only see these oranges and reds, but these others can get picked up by this thing called a spectroscope, okay? The black, the dark areas, those are spots where helium is not allowed to exist as far as that electron giving off light. Okay, these colored areas, those are the wavelengths that are allowed to be released for helium to get back down to its safe spot, to its ground level. So the emission spectrum is very unique. It's its own fingerprint for every single element. Whatever nickel gives off is different than the emission spectrum for nitrogen. They each give off their very own. In fact, let's play around a little bit. Let's just do an emission spectrum of elements. I don't know what we'll get. Be nice if there's like a periodic table of the emission spectrum. Oh my gosh, like look at this. I was just asking and then look at this one. Look at this, children. Look. Specific fingerprint of each one. So we're going through the periodic table. Look at this. Hydrogen, there's its fingerprint. Helium, there's your fingerprint. Lithium, beryllium. Everybody has their distinct fingerprint of light. And I'm going to call these elements bodies. Every element gets a specific fingerprint of the light that it gives off when we energize that atom. The electrons get excited. They get the caffeine jolt, and then they give off these unique colors of light. That is going to be key in how the electron behaves and what's going on. All right. What do I mean by that? Okay. We're back to looking at Bohr versus Rutherford. Remember, two very, very different ideas. Rutherford thought that the electron could exist, that it went around the nucleus. Wrong. Like, we're going to realize that's such a lie. Rutherford, nice try. You're still smarter than me, way smarter than me, but you were wrong. Bohr, he also thought electron goes around the nucleus. Wrong. But how it went around the nucleus is very different. Rutherford thought that electron could exist at any orbit, any distance from the nucleus. There's no problem, any distance. Bohr, mind you, was a student of Rutherford's, a very good student, because he was trying to prove that his professor was right, his researcher was right. They're in the same lab. He's working under Rutherford. He helps with the gold foil experiment. And Bohr all of a sudden realizes, my teacher's wrong. Like, Rutherford, you're not right. This electron can't exist anywhere. And I'll show you why. Like, what would happen if it actually did? It has to exist only at specific areas, specific allowed orbits from the nucleus, okay? The emission spectrum was the clue for this. As soon as they were able to see the emission spectrum for different elements, it really shed light on the topic of what's really going on. Okay, that's the funniest thing I've said this entire time. So this was a video clip that you watched. Here is a really bad attempt of me trying to explain what's going to go on. So even though it looks like different cores of the Earth, what this really is, this little black part here, this is the nucleus. Yes, I want you to be awful and actually attempt to draw this. So this is the nucleus. We're trying to go with the whole Roy G. Biv thing, right? Okay, red, orange. Oh, there's orange somewhere in there. Yellow, green, blue, purple. I don't really know what indigo is, so I just pretended like that was indigo. If Rutherford was right, then those electrons could exist. Imagine that this red is made up of tons and tons and tons of red rings around the nucleus, okay, that are just smushed on top of each other. The yellow or orange, pretend like there's orange somewhere in there and yellow. Tons and tons and tons of individual rings that are just packed right next to each other. Same thing with the green. Rutherford believed that electron could orbit any distance from the nucleus. Okay, hit pause, draw it, whatever. Let's go over here. Bohr believed This is your little nucleus with where your protons and neutrons are packed. Bohr said, nope, sorry, Rutherford. I wish you were right, but here's the truth. This electron can exist here in this orbit, or it can exist here in this orbit, but it's not allowed to be anywhere in between. Okay, so it could be here, or it could be here, or it could be in the green, or maybe it could be in two separate purples, but it's not allowed to exist anywhere in between. So take a moment to draw that. Okay, once you're done with that, and I don't want to go to the next part, but we're looking at these two questions, but I need us to be able to see these pictures. So if Rutherford's right, okay, pretend like, this is helium. We know helium has 2 electrons. And let's say that one of those electrons really likes to hang out right here. Oh, son of a gun. So hopefully you can see my mouse. So this is where the electron likes to hang out. We give it electricity. We give it heat. We give it electricity. And next thing you know, that electron, it's this caffeine jolt. It goes away from home and it's hanging out way here in the purple area. So it's far, far away from the nucleus. That electron, now Rutherford thinks it's spinning around. I'm kind of scared to try to attempt it. So yeah, see, I can't do it. So it's hanging out way here and it doesn't want to be there anymore. It's burned off its energy. It wants to get rid of its energy. It needs to go back home. If Rutherford was right, remember where home is all the way down here in the red. If Rutherford was right, then as it goes back home and it's releasing its energy, we should see every single color of the rainbow, right? In the emission spectrum, every single color, a smear. I liked how that guy said that in the video. Smear of color as it went back home to this red zone, if Rutherford's right. Let's go over here. Bohr, we've got this little electron hanging out in the red. So electrons here in the red, and I wish all of a sudden I could just ploop my little arrow over to the purple. We give it energy. We give that same, oh my gosh, it disappeared, kind of like what we talked about. We gave it energy and it jumped. Wouldn't that be awesome if I said, look, just landed in the purple. It went straight from red to the purple, didn't go in between. Let's pretend like it's still there for a second. Oh my gosh, children. So it's right here in the purple. Now, it loved hanging out there for a little bit, but it wants to go back home. How does it go back home? Well, it goes back home by releasing energy in the form of what? In the form of light. Bohr says it's only allowed to release certain packets of energy as it goes back home. And maybe, let's see if I can get to disappear again. So it's wanting to go back home. And what's the very next allowed energy it can give? Green. That was my attempt of trying to get it to go there. And then it doesn't quite want to hang there in the green. Now remember, this happens in splits of milliseconds. Doesn't really want to hang out in the green. What's the next color it might give off? That's supposed to be right on the red. Red. Nothing in between the green and the red, just straight off red. And that specific wavelength, it's not quite back home. It needs to get back to what? The boom. That was supposed to land right on that one. Okay, that's what you saw, I'm sure. And it gives off that energy and it's finally back home. So it has to jump from one wavelength of energy, gives off that energy, gives the next, gives the next, gives the next. Now, for those of you that are going, wait, what? That one electron literally jumps down the stair. It doesn't. I'm kind of lying. Here's what's really going. Am I just releasing one atom? Am I just electrifying one atom of helium? No, I'm electrifying tons of atoms of helium. And as they jump, and they might go to different energy levels as we're exciting it. And it's releasing those energies, those different electrons, it's releasing those specific quantas of energy as it's going back down to its ground state. So let's review. If Rutherford was right, it would have released that electron to get to ground state, a smear of color, a rainbow of color as it went back down to its healthy home state. If Bohr was correct, it would release only specific lines, specific colors of light, from the purple to the green to the darker red to the less darker red. Okay, so let's fill that part in. So what would always be the emission spectrum under Rutherford? We would have seen a blurred rainbow. What would be an example emission spectrum with Bohr? We would see specific lines of color, specific lines of light. Okay? What about this next part? What would always be the color of light we would see for a flame test? If we were to look at a flame test, or, and I know you guys didn't get to use a spectrotube, but that's basically the thing that shows you these lines of light. If Rutherford was right, for every single element on a flame test, it would be so boring. It would be white light. It would be like what you see is just white light, boring. I throw copper into the fire, whoop-de-doo, just boring old white light, doesn't do anything. We throw copper in the fire, we see green light. Like, that's telling me something specific. If Bohr is correct, what do we see for each atom as we excite it for a flame test or looking under a spectrotube, which again, I know you guys didn't get to play with. Maybe when you come back, you'll get to. We'll see specific colors of light, which is exactly what we see. Copper gives off green light. Strontium gives off red light. Lithium gives off, I think, red light. Mercury gives off purple light. Not that we should burn mercury, but we see specific colors. All right. Oh, I think we're going to pause there because you're probably very sick of hearing this. But, you know, this is a thinking, more listening and thinking than it is writing with this particular video. And then we're going to have a lot of fun really helping you understand this. Ms. Marcus and I jumped out of our comfort zone in a big way, and we'll be showing you that, I'm sure, very soon. All right, you guys take care, and we will see you later.